Let's talk about a tiny component that is responsible for smartphones, the internet, electric cars, or modern technology in general. They are called diodes. A diode is basically a semiconductor device that allows current flow in only one direction, from anode to cathode. For this to happen, we have to have the positive terminal of the power source on the anode of the diode, and the negative terminal on the cathode of the diode. This way the diode is forward biased and will conduct. If the voltage reverses, the diode becomes reverse biased and blocks off the current from going the opposite way. This single property makes the diode very useful for various applications. There are many types of diodes, and each has unique properties, hence unique uses. Some are LED, light-emitting diode. They emit light when forward biased. We have the rectifier diode. They allow current flow in one direction when forward biased, and blocks it when it reverses. That's reverse biased. There's also the Zener diode. This one has the capacity to conduct in reverse bias when a specific breakdown voltage is reached, so usually it is used as a voltage regulator by connecting its anode to ground and its cathode to the node that is to be regulated. So, let's assume this diode has a breakdown voltage of 5 volts. If the voltage at the cathode rises up until it gets to 5 volts and tries to exceed it, the Zener diode conducts current to ground to effectively keep the voltage at the required threshold. They are usually rated by their breakdown voltage. Schottky diodes. These diodes have very fast switching speeds. They switch from conducting to blocking at fast speeds and are used for high switching alternating currents. Let's go back to the rectifier diode and how it converts AC to DC. First, let's look at a check valve. It's a one-way valve. It allows fluid through it in only one direction. If flow comes from the opposite direction, it blocks it. This is exactly what the diode does to current. When forward bias current flows, if reverse bias current is blocked. If a diode is placed in an AC circuit, whose waveform is as shown, given the fact current changes direction multiple times a second, the waveform becomes this. And that's because the diode clips off all the current flow that should happen. When it's reverse bias, it only allows the positive flow happen, and as soon as the current is about to change direction, at 0 amps it blocks it off. This is called half-wave rectification. We then have a current flow that doesn't change direction, but is bumpy. Can't actually pass for a direct current. But this we can smooth it out by adding a capacitor. It will charge until the waves peak, and discharge when the waves decay, filling up to give a smoother wave. In situations where higher efficiency or higher power and smoother DC output is needed, we can make use of the bridge rectifier. It is a smart arrangement of four diodes, usually called a full-wave rectifier, to utilize current flow from both directions while converting AC to DC. So instead of this, which we had in the half-wave case, we now have this. And if we compare it to the original sine wave, we can see it converts the negative current flow to positive, and that's because as current flows from this direction, it gets to this node, it's blocked by this diode. But it can flow through this, which is the forward bias diode, and then goes into the circuit as DC. When alternating current comes from this part, it is blocked by this, and transmitted by this into the circuit. So we have a continuous positive wave, so we have the positive flow of current coming from the life of the AC source. And then we have the reverse current coming through the neutral into a diode. That still leads it into the positive of the circuit. So we have both waves on the positive side. If we introduce a capacitor to this, we have a smoother DC wave than we had with the half wave. If we add an additional load to the circuit, we have more ripples show up. But putting the same load on the half-wave circuit, we have this, which shows the bridge rectifier is a better choice for high-power applications. Okay, so I have a simple setup here. I have the rectifier diode and I have a resistor, a 1 kilo ohm resistor. I have a 12-volt transformer. I want us to see exactly what we have just talked about, and what the waves will look like if we connect these together. So I have one probe to read the input wave, the input signal coming in from the transformer. I have the other one to read the output of the diode. We're going to be seeing the voltage across the resistor with that one. This is the input signal coming in from the transformer. You can see we have 12 VRMS and 35 peak-to-peak volt. So if we look at the output of the diode, of course this is a half-wave rectifier. If we look at the output, we see we have the negative part of the waves cut off, so the diode allows for current to flow from the positive direction. And once the current is about to change direction, it blocks it, and so we see a straight line there. So what if we choose to add a capacitor? 'Cause of course we have bumps, which makes this not a perfect DC. We're going to put in a capacitor to charge on the rise of the wave and discharge on the fall, so it can fill up the space we're having there. So we have an almost straight DC. So let's get to view this better. So we can see that we have ripples. Okay. It's not a perfect DC, we have ripples, and we see that those ripples come from the crest of the wave. So if I bring back the output of the transformer, you would see that those ripples come from the crest of the wave. So the capacitor is discharging to fill up the lapse for when the current begins its fall. It's not a perfect DC, but it's good enough, of course, to power some level of load. So let's try with the bridge rectifier. So we have our bridge rectifier connected, and we're going to be reading just the output of that. So we turn it on, and we see what we have as a voltage. We see we don't have straight line spaces in between waves. So this is a more efficient supply, and this will definitely produce more power compared to the half-wave kind, which means you'll be able to bear more load. So let's bring in our capacitor here, and let's see what the wave is going to be like. So if we turn that on again, you see we have a smooth wave. Okay, so if we bring this down to 5 milliseconds, like we did before, we can see we don't have that much ripple as we did with the half-wave kind.